Hello, I'm John Doherty. This video covers two topics, both of them at a very basic level. It starts off by looking at matrices and vectors. It then provides a very basic introduction to statistics in order to show how random variables can be manipulated through simple matrix equations. Do not be daunted, the material covered by this video is easy. Understanding it will lay the foundations for understanding more complex topics such as singular value decomposition and linear analysis. These topics are covered in other videos. Thanks. In this talk, we'll cover some basics of vectors and matrices on the one hand, and later in the talk, we'll also cover some basics of statistics. Now, you don't have to know much about vectors and matrices, about linear algebra to use PEST. In fact, you don't have to know anything. However, in some other videos, we'll cover some of the theory behind PEST, and knowing some basics of matrix manipulation and some basics of statistics will help you understand that theory. It's more the principles than the details of the mathematical operations that are important here. So don't worry if you don't remember everything. All that's important is to understand a few basic principles. So let's start with a vector. Now, a vector is just a container full of numbers. In this case, we have an n-dimensional vector x, and it's called n-dimensional because it holds n numbers. These are its n elements. If we have a three-dimensional vector, then we have 3 elements. And probably most of you will remember from school that often a vector was depicted as an arrow. And in small dimensional spaces, 2 or 3 dimensions, a vector can indeed be depicted in this way, with the elements of that vector, x1, x2 and x3, being the coordinates, the projections of that vector onto each one of the coordinate axes. Once we know x1, x2 and x3, we have the coordinates of the vector and can construct the entire vector. The magnitude, or sometimes called the norm of a vector, is calculated using this equation. The square root of the sum of the squares of the elements of the vector. This is the same as the length of the vector. The same applies in n dimensions as applies in 3 dimensions, but it's easier to picture these things in 2 and 3 dimensions than in n dimensions. If a vector has a magnitude or a length of 1, it is called a unit vector. Now let's turn our attention to matrices. Matrices are also containers full of numbers, but they're 2-dimensional, and sometimes more, but mostly 2-dimensional containers full of numbers. A 5 by 3 matrix has 5 rows and 3 columns. So each element of the matrix has indices which tell us about the row and column to which the element belongs. A 3 by 2 matrix obviously has 3 rows and 2 columns. Again, each element is indexed according to its row and column. While matrices are somewhat useful to hold arrays of numbers, mostly those numbers are used in operations. Normally a matrix is used to operate on a vector to produce another vector, and more often than not, that operation is a matrix multiplication. So here we're saying that the vector y is obtained from the vector x through multiplication of x by the matrix y. If the matrix A is a 3 by 2 matrix, as it is in this case, then the vector y will have 3 elements, the same as the number of rows of A, and the vector on which A operates, in this case x, must have 2 elements, the same as the number of columns of A. Each element of y is formed from the elements of x through this operation, so that y1 equals a11x1 plus a12x2. That is a linear operation, sums with each part of that sum being formed by a multiplication of an element of the matrix and the element of the vector. So we can look at matrix multiplication in 2 ways. The first is, as I just said, to form element y1, we go along the row and down the column, multiplying and adding. The same for y2, the same for y3. Or we can look at it another way. We can say that this matrix A can be thought of as having vectors in its columns. So this 3 by 2 matrix A, we can say has a 3-element vector in its first column and a 3-element vector in its second column. We form the outcome of this matrix operation by adding these vectors and multiplying by these coefficients. That is, the final vector y is the first vector in A times x1 plus the second vector in A times x2. Not only can matrices multiply vectors, matrices can multiply matrices as well. This involves summations and additions, but the easiest way to think of matrix multiplication is simply the fact that it implies 2 matrix on vector multiplications. That is, we could say C equals ABX as we do here, or we could first say Y equals BX, then Z equals AY, and it's the same as saying Z equals ABX. The transpose of a matrix is simply the matrix flipped on its side. We interchange the rows and columns of A to obtain AT. We designate the transpose by this superscript T. If we take the transpose of a matrix, we end up with the original matrix. A square matrix has the same number of rows as it does columns. A symmetric matrix is a special type of square matrix. A symmetric matrix is such that the matrix is equal to its transpose. Another way of saying that is that it is symmetric about its diagonal. That we can interchange rows and columns and end up with the transpose of the matrix, and that transpose is equal to the original matrix if interchanging rows and columns does not actually change the matrix. A diagonal matrix is a special type of symmetric matrix that, as the name implies, has 0 as its off-diagonal elements and along the diagonal we have non-zero elements. A special type of diagonal matrix is the identity matrix. It has ones down its diagonal. And the identity matrix has some special properties. If we multiply a vector by the identity matrix, it leaves the vector unchanged. If we pre- or post-multiply a matrix by the identity matrix, it leaves the matrix unchanged. Inverse of a matrix. Now this is getting close to the heart of what PEST is all about. Suppose we have this relationship that the vector y equals the operation of A on X. Suppose also that the matrix A is square. Then, if we want to back calculate X from Y, this is the relationship we have to use if the inverse of the matrix A exists. So if a matrix is square, it may or may not have an inverse. We specify the inverse as A with that -1 superscript. If that inverse exists, we can calculate X from Y using that operation. Mathematically, the inverse of a matrix is defined using this relationship. A times its inverse is equal to the inverse of A times A equals the identity matrix. And to see how that applies, consider Y equals AX. Let's pre-multiply both sides of this equation by the inverse of A. So A-1A times Y equals A-1A times AX, just from this equation. But A-1A equals I. By definition, IX equals X because I is the identity matrix. So, as I said before, a matrix has to be square if it's going to have an inverse. But just because it's square doesn't mean that it does have an inverse. If a matrix doesn't have an inverse, it's called singular. If a square matrix does not have an inverse, it's called singular. And the inverse of a matrix is the original matrix. Now we can consider a vector as a type of matrix. So here's a vector we looked at before, X, with its 3 elements. We can also consider X as a 3x1 matrix. And as such, operations that we can perform on matrices can be performed on vectors. One such operation is transposition. So here's our 3x1 matrix X. Here's the transpose of X, which is a row vector, a 1x3 matrix. We can use XTX to calculate a number which is actually the norm of X squared. So whereas before we calculated the norm of X using this relationship, we can write it more simply using this matrix operation, XTX equals the norm of X squared. Now let us consider orthogonal vectors. Here are 2 vectors, X and Y, each with 3 elements. X is orthogonal to Y if XTY equals 0. In small dimensional vector spaces, we can characterize that as the x being perpendicular to y. It has a zero projection onto y. We can look at matrices, as I said before when we were talking about matrix multiplication, as sets of vectors. We can consider each column of a matrix as a vector. So we can write big V here, the matrix, as little v1, little v2, little v3. And something I forgot to say before is that when we're talking about vectors, we give them normally a lowercase letter. We normally make it bold to specify that it's a vector with a lowercase letter. We normally specify a matrix with an uppercase bold letter. Anyway, in this case, our matrix V can be considered as vector v1, v2, v3, and here's each one of these vectors. They are simply the columns of big V. An orthonormal matrix has some special properties which in other slideshows we will see give us the ability to do some very powerful things. Considering our matrix here as, once again, sets of vectors, each column is a vector. A matrix is orthonormal if the vectors which comprise its columns are orthogonal to each other, and if the vectors which comprise its columns are unit vectors. And we can do some wonderful things with orthonormal matrices, as we'll talk about in another video. Because the columns of an orthonormal matrix have these properties, they're orthogonal to each other and they're unit vectors, we can think of the columns of an orthonormal matrix as defining a new coordinate system in our vector space. Here's the original coordinate system, oriented along the directions to which the elements of a vector pertain. Here's new coordinates, defined by unit vectors that are orthogonal to each other, these comprising the columns of our orthonormal matrix. Now, the orthonormal matrix has some beautiful properties. One of the most useful of these properties is the fact that to obtain the inverse of an orthonormal matrix, all we have to do is to obtain its transpose. Hence, VTV equals VVT equals the identity matrix. We can partition any matrix, but we're just focusing on an orthonormal matrix at the moment. We can partition any matrix into submatrices. If we partition this orthonormal matrix, in this case it's 3 by 3 orthonormal matrix, as shown by the red line, then we can define two subspaces of our vector space. The first subspace is spanned by the unit vectors v1 and v2 in this case. The second subspace is spanned by the vector v3. So we can write big V as v1, v2. These are orthonormal matrices which have unit vectors comprising their columns that span subspaces of parameter space. v1 equals little v1, little v2, and in this case v2 has just one vector, v3. Now, of course, when we're working with parameter estimation and solving inverse problems, our vector spaces are going to be much larger than 3, but describing this using 3 dimensions allows us to draw pictures. So here's the picture we had before with little v1, little v2, little v3, the columns of our orthonormal matrix. And here's the subspace spanned by little v1 and little v2, and that, as we saw before, are the vectors which comprise this matrix. So v1, big V1, represents the 2-dimensional subspace of 3-dimensional vector space characterized by this plane. Meanwhile, the V3 matrix has only 1 dimension, and it characterizes this orthogonal subspace to this plane. Some further important relationships which we'll use in other videos. Here's V1, the matrix we obtain by the partitioning defined by this red line. Here's the transpose of V1, where we've simply flipped the rows and the columns. A lovely relationship is this one. V1t V1 is equal to the identity matrix. A 2 by 2 identity matrix in this case, because V1 has 2 columns. If we do the matrix multiplication the other way round, we have a 3 by 3 matrix as the outcome of the matrix multiplication. This is not an identity matrix in this case. However, it has some very nice properties. This, in fact, is an orthogonal projection operator onto the subspace defined by V1. So, here's an arbitrary vector in our 3-dimensional parameter space, our 3-dimensional, vector space, because we're not talking about parameters yet. Here is the projection of this vector P onto the subspace defined by the V1 matrix, and it's obtained by pre-multiplication by this orthogonal projection operator V1 V1t. We can do the same for the orthogonal subspace, which in this case is 1-dimensional, and I'm sorry, that should be V2 V2t P. Now I want to talk a little bit about statistics. Not much about statistics, because as I said previously, you don't have to know too much about statistics to use PEST. However, there are some things that you do need to know, and we'll cover these now. Consider that I've got 2 random variables. I'm going to call them x1 and x2. Each of these actually has a uniform probability distribution. We'll talk more about what that means in a moment. But I use my computer to generate realizations of x1, and every time I generated a realization of x1, I generated a realization of x2 as well, and then plotted it up. Each one of these dots corresponds to a realization of x1 and a realization of x2 plotted according to the x1 and x2 axes. Now, if I want to get the probability distribution of x1, I can move along the x1 axis here, and in each one of these rectangles I can count the dots. And this tells me about the propensity for the random variable to fall within this interval of x1. And this is telling me something about the random variable x1. The thing about random variables is I can never know what its value is, but I know something about a random variable, and the way to characterize a random variable is to say what is it most likely to be doing? What are the values that it has with a high probability? What are the values that it cannot have? Or what are the values that it has with a low probability? And by doing that, I've characterized that variable. I've said as much as I can say about it. Now in this case, by counting the dots, I soon realized that x1 has a uniform probability distribution, that it's just as likely to take on this value as this value as this value, but it will not take on a value greater than x1 max, and it will not take on a value lower than x1 min. I'm calling this the marginal probability density function of x1 because I don't care about x2. It can take whatever value it likes. All I am doing is focusing on x1 and x1 alone, regardless of what x2 does. Now in this particular case, x2 is independent from x1, so the marginal probability distribution of x1 is the same as its total probability distribution. We'll refine this concept a little bit more later. So there's the probability density function, or PDF, of x1. And an important property of probability density functions is that they integrate to 1. The area under that curve is 1. And this then is all we can know about the random variable x1. I can do the same for x2. Again, I can count the dots to see if there's a bigger chance that it lies here rather than here. I find that there's pretty much the same number of dots in every one of those rectangles. So I can then conclude that x2, like x1, has a uniform probability density function. There's as much of a chance of it having this value as this value, as long as those values are between x2 min and x2 max, but there's no chance of x2 having a value above x2 max, and no chance of it having a value below x2 min. Once again, the area under the probability density function is 1. I could construct a two-dimensional probability density function, this time taking both of these variables into account. So now I'm looking at the joint probability density function of x1 and x2, and this time when I'm counting dots within squares. I quickly find that there's pretty much the same number of dots within each one of these squares, and hence that the joint probability density function of x1 and x2 is uniform. Uniform for x1, uniform for x2, uniform for both of them, and the integral under that probability density function is again equal to 1. Okay, that's easy. Now let's look at a slightly more complicated situation. Here I've got x1 again, and I've got x2. And this time I use my random number generator to generate realizations of x1 and of x2, and I find that they're not independent anymore, and we'll look into that a little bit more shortly. But obviously this cloud has an orientation. Obviously the value of x1 seems to be related to the value of x2. But x1 and x2 are still random because I do not know their values, but their probability density function needs to reflect the fact that they're obviously not independent. Let's start off this time by examining the joint probability density function of these two random variables. So within each one of those squares, I count the dots. There is my joint probability density function. These are multinormal variables, so this is a bell-shaped curve in 2 dimensions. The volume under that probability density function is 1, as it has to be. Now let me focus on the marginal probability density function of x1. When I say marginal, once again, I don't care what x2 does. I'm just going to generate my paired random numbers, but only focus on x1 when I'm trying to come up with a probability density function for a single random variable x1, and I don't care what the paired value for x2 is. So in determining the probability density function for x1, I count the number of dots in this series of rectangles, and I find that it's got a normal probability density function, a bell-shaped curve that we're all familiar with. Once again, the area under the probability density function is 1. And from this probability density function, I can determine the mean of x, and I can determine the standard deviation of x1. And for a normal variable, that's all I need to characterize x1, its mean and its standard deviation, and the fact that it's normally distributed. In fact, there's nothing more I know about it than that. I don't know its value, but by knowing its mean and its standard deviation, I know about its behavior, I know about the values that it's more likely to take, and I know about values that it's less likely to take. We can do the same to come up with the marginal probability density function for the x2 variable. Once again, I count the dots. Come up with the marginal probability density function of x2, characterized again by the mean and the standard deviation of x2. Now when I've got these two random variables, x1 and x2, if I'm going to come up with a set of numbers, a small set of variables that characterize their joint probability distribution, I need more than just the mean of x1 and the mean of x2, and the standard deviation of x1 and the standard deviation of x2. Obviously, there is statistical interrelatedness between x1 and x2, which needs to be taken into account in formulating any description of their joint probabilities. Now, this can be looked at in a number of ways. x1 and x2 are obviously not statistically independent. And what that means is if I know x2, just say I acquired the value of x2 from the joint samples of x1 and x2, and just say that x2 is equal to a. Well, suddenly I know something about x1. This probability distribution for x1 is called the conditional probability distribution for x1, conditional on knowing that x2 is equal to a. x1 has a conditional mean. It's here. It's not its marginal mean. And x2 has a standard deviation which is narrower than its marginal standard deviation, which is another way of saying that knowing x2 tells me something about x1 which is another way of saying that the uncertainty associated with x1 is now reduced. This is an outcome of the statistical interrelatedness of x1 and x2. Similarly, if I know that x2 is equal to b, I have a different conditional mean for x1. Because they're correlated, and if x2 is equal to c, I have a different conditional mean for x1. They are not independent. The value of one is not a function of the other, because knowing one doesn't tell me exactly the other, but knowing one tells me something about the other, and that something is expressed through a refined probability distribution for the other, and that refined probability distribution is called the conditional probability distribution. So we need to characterize this if we're going to give a simplified statistical description of x1 and x2 together. So, as we said before, if it's just x1, we need the mean and the standard deviation. Here they are, the mean of x1, I'm calling that mu1 here. And here is the standard deviation of x1, but I'm actually going to square that, and I'm going to call it the variance of x1. Variance is a little bit more convenient to use as a description of stochasticity for reasons that we'll find out shortly. It's just the standard deviation of x1 squared. Now, to characterize two random variables, though, we need to go a little bit further. Yes, we need the mean of x1 and the mean of x2, which I'm calling mu1 and mu2 here. And here's the variance of x1, sigma squared 1, 1, I'm calling that. Here's the variance of x2, sigma squared 2, 2, I'm calling that. But I'm using a matrix now, a 2 by 2 matrix, because I have two random variables, x1 and x2. And that matrix has off-diagonal elements, sigma 1, 2, sigma 2, 1, which are actually the same. And it's these off-diagonal elements which are telling me that x1 and x2 are statistically interrelated. So I have to move now to a description of x1 and x2 collectively, which takes account of their statistical relatedness, and I replace the variance of x1 and the variance of x2 with a covariance matrix which includes a term which specifies their degree of statistical interrelatedness. This matrix, this 2 by 2 matrix, sometimes called the variance-covariance matrix, often simply called the covariance matrix for short. The diagonal terms, as I just said, specify the individual variability of the individual parameters, the square of their standard deviations. The off-diagonal terms, which are equal to each other, specify the amount of statistical interrelatedness between those two random variables. The fact that this cloud is a little bit narrow, and the fact that it has a direction in vector space. It reflects the fact that knowing x1 tells me something about x2 and vice versa. If that cloud didn't have a direction, as it doesn't in this case, then x1 and x2 are not statistically interrelated, which means that the covariance matrix which I use to specify the joint probability distribution of x1 and x2 has 0 off-diagonal elements. I still use a covariance matrix, but its off-diagonal elements reflect the fact that for that case there is no statistical interrelatedness between x1 and x2. Let us now extend what we've been talking about into n dimensions. Suppose I have a vector x with n elements. So we're working in n-dimensional vector space. Suppose that these n elements are random. Then x is a random vector. As such, to characterize the stochasticity of this random vector x, we need to know its mean and we need to know its covariance matrix. The same principles apply in n dimensions as applied in the smaller number of dimensions that we were discussing a moment ago. Each element of this vector here, and I'm using an underscore to denote mean, each element of the mean of x is the mean of the respective element. The covariance matrix of x is an n by n square matrix. If x has n elements, Cx is an n by n matrix. The diagonal elements of Cx express the variance of each of the elements of x. Remember, variance is the square of standard deviation. The off-diagonal elements of Cx express the degree of statistical interrelatedness between respective elements of x. A covariance matrix has some important properties of which we should be aware. As we just said, if it describes a vector x which has n elements, then Cx must be an n by n matrix. It must also be symmetric, but more than that, Cx must be positive definite. Positive definite means that this relationship applies. Whatever values are taken by the elements of the random vector x, then xtcxx will always be positive. That's a powerful relationship, and it demarcates a positive definite matrix from any other type of matrix. We can't just say any n by n matrix is a covariance matrix. It has to be positive definite or it cannot be a covariance matrix. Finally, if a matrix is positive definite, it can't be singular, it will have an inverse. Finally, suppose that we have a vector y calculated from a vector x using this matrix relationship. Suppose that x is a random vector and that we've characterized x by its mean and covariance matrix. Because x is a random vector, then y must be a random vector. Furthermore, we can characterize the randomness of y through two matrix equations. The mean of y is simply a times the mean of x. The covariance matrix of y is calculated from the covariance matrix of x using this equation. Hence, if we know the stochasticity of the random vector x, we know the stochasticity of any vector y, which is also random, and which is calculated from x using a matrix multiplication. Thank you.